Hi, welcome to my channel. I am Deepak.R, studying in Sri Venkateswara College of Engineering from the Department of Computer Science and Engineering, Cybersecurity. Today, I am going to explain about De-Broglie hypothesis and matter waves. Introduction. Welcome to our presentation on De-Broglie hypothesis and matter waves. Louis de Broglie was a French physicist and Nobel laureate. In 1923, he was inspired by Einstein's work on the dual nature of light, wave-particle duality. In 1924, Louis de Broglie proposed a groundbreaking idea that led to the unification of the particle and wave nature of matter. De Broglie postulated that if light could exhibit both wave-like and particle-like properties, then perhaps particles could also behave as waves. Let us explore the De-Broglie hypothesis and its implications for our understanding of the fundamental nature of particles. Wave-particle duality. Wave-particle duality is the concept that particles can exhibit both wave-like and particle-like behavior. The phenomenon like interference, diffraction, and polarization are attributed to the wave properties of radiation. The quantum theory of radiation and experiments like photoelectric effect and Compton effect describe the particle nature of radiation. Thus, radiation behaves like both waves and particles under different suitable circumstances. Hence, radiation exhibits dual nature. De Broglie hypothesis. In the year 1924, French physicist Louis de Broglie extended wave-particle dualism through a hypothesis stating if radiant energy could behave like waves in some experiments and particles or photons in others, and since nature loves symmetry, then one can expect that the particles like protons and electrons to exhibit wave nature under suitable circumstances. This is well known as de Broglie hypothesis. Equation for de Broglie wavelength. De Broglie associated a wavelength with a moving particle which is known as the de Broglie wavelength. The equation is lambda is equals to h by p or lambda is equals to h by mv, where lambda is de Broglie wavelength, h Planck's constant, p momentum of the particle. Matter waves. In his 1924 doctoral thesis, De Broglie proposed that all matter particles including electrons, protons and atoms possess both particle and wave properties. He introduced the idea of matter waves, which is called pilot waves that accompany particles they move through space. The waves associated with moving particles is known as matter waves. The wavelength associated with matter waves is called de Broglie wavelength. Properties of matter waves. Matter waves are associated only with particles in motion. They are not electromagnetic in nature. Group velocity is associated with matter waves. As a result of superposition of large number of component waves, which slightly differ in frequency, matter waves are localized. The phase velocity has no physical meaning for matter waves. The amplitude of the matter wave at a given point is associated with the probability density of finding the particle at that point. The wavelength of matter waves is given by lambda is equals to h by mv. Implications of the de Broglie hypothesis. Wave-particle duality. The de Broglie hypothesis was a significant step in establishing the wave-particle duality concept. Unification of physics. The de Broglie hypothesis unified the theories of classical mechanics and quantum mechanics. Quantum mechanics. The concept of matter waves played a pivotal role in the development of quantum mechanics. a branch of physics that describes the behavior of particles at the atomic and subatomic scale. Wave functions. The matter waves are described by complex valued wave functions in quantum mechanics, electron microscopy, and diffraction. The concept of matter waves has practical applications such as in electron microscopy. Experimental evidence supporting the de Broglie hypothesis. The concept of matter waves was experimentally confirmed by the Davison-Germer experiment in 1927. Their experiment demonstrated that electrons, which are considered particles, behaved like waves when passing through a crystalline structure. They observed electron diffraction patterns similar to the diffraction of light waves. This experiment provided direct evidence for wave-like properties of particles. Applications of the de Broglie hypothesis. The de Broglie hypothesis laid the foundation for the development of quantum mechanics. It is a crucial concept in understanding the behavior of particles in various quantum systems. Matter wave interference has a practical applications such as in electron microscopy and diffraction techniques to achieve higher resolution. The development of electron diffraction techniques has revolutionized the study of crystal structures. The concept of matter waves has also been applied to the field of quantum mechanics and particle physics. Conclusion. The de Broglie hypothesis revolutionized our understanding of the dual nature of matter and energy. Matter waves associated with particles exhibit wave-like behavior and can be described by their wavelengths. The de Broglie hypothesis has had significant applications in various fields of science such as electron microscopy and quantum mechanics. It unified the wave and particle nature of particles, leading to the development of quantum physics. Today, the de Broglie wavelength continues to be a fundamental concept in modern physics. Thanks for watching.